Yes.
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 If we don't convert it to x, like you see in our mind.
Convert it to x.
Convert into x while using the limit.
What are you talking about?
Or like we did it on the video. Yeah, not well, not L'Hopital only, but for like the limit itself, because you know you can't plug in infinity for n.
Yeah.
You're gonna take off of that even if we don't see it in our mind.
Are you talking about the improper integrals, or are you talking about sequences? I think I know what you're talking about. Let me go through today, and then if we're talking about the same thing, I'll answer your question. Okay, a lot to do today. Y'all ready? Video is recording, audio is working. All right, so last time I sent you home with some homework, I said you'd probably run into some issues. So let me get through the rest of today's stuff, and then that might help you with the homework, all right? But one of the main things that we talked about last time is that if you take the limit as n goes to infinity of some sequence a sub n, if that equals L, right, then we say that we say the sequence, what? Converges. Right? Otherwise, we say it diverges. So we're doing limits again, and this is from Cal 1, and that's why you're going to need some things from Cal 1 that I know some of you saw, some of you didn't, from show of hands back when we were talking about L'Hopital's rule in the improper integrals. So please review L'Hopital's rule. All right, please review L'Hopital's rule. And I'm going to send an email out, I promise, okay, by the end of the week. I'll try and do it today. That with videos from my Cal 1 where I talk about L'Hopital's rule. All right? Now, the problem that we have with L'Hopital's rule is that L'Hopital's rule involves taking derivatives of functions, and sequences are not continuous functions. We did discuss this a little bit last time. So I want us to start our first problem today with trying to find, does the sequence a sub n equals natural log n over n converge? All right, does it converge? So that means we need to take the limit as n goes to infinity, right? So we take the limit as n goes to infinity of natural log n over n. And then we ask ourselves, what does the natural log do as n gets bigger? So if I look at just natural log, we know that natural log looks like this, right? That's what y equals natural log of x looks like, back from Cal 1, or from college algebra, in fact. Natural log of n means we're only plugging in, 1, 2, 3, 4. So when we plug in 1 into the natural log, what's natural log of 1? 0. And then whatever natural log of 2 is, a natural log of 3, a natural log of 4, and so on and so forth, right? So we know that since natural log of n, or natural log of x goes to infinity, right? Natural log of n should also go to infinity. So as you go out to the right, it gets higher and higher and higher, yes? And then when we look at the bottom, of course, if n goes to infinity, that denominator gets bigger also. So what you have in this case is something that looks like this, infinity over infinity. And back in Cal 1, we'd say, oh, that's perfect for L'Hopital, right? Perfect. Infinity over infinity, use L'Hopital. But like I just said, L'Hopital requires you're dealing with nice continuous functions, not a bunch of dots. So we have an important theorem, all right, in this section. It's on page 428. It's theorem 3 in this section. And it says this, roughly, okay? It says if the limit as x goes to infinity of f of x equals L, where x is an element of the real numbers. So let's say you're taking a limit and you're letting x go to infinity, and you have f of x. This right here is a function of x, and x is a real number. So basically this is saying back when you're looking at a Cal 1 function, right? Not just picking off single points. You're letting x be any real number, right? So if the function goes somewhere over all numbers, all real numbers, as x goes to infinity, then what should happen? I mean, you can kind of see it from here. If the red goes somewhere, then the blue is going to have to go there also, right?
Yeah.
So whatever the function does, the sequence must also do. Right? Seems obvious, but you have to prove it, and there's a theorem. You don't have to prove it. It has to be proven, and so there is a proof for it. So if that is true, then the result of the theorem is that the limit as n goes to infinity of f of n must also equal L, where n is an element of z positive. So that means you're in positive integers. And what is it from last time when we took a function and we restricted its domain to just the positive integers? That was a sequence, right? That was the notation we used. Instead of saying f of n, we said, oh, a sub n, and that everyone knows we're talking about a sequence. All right, so how is that going to help us with this example? So back to the example. We're trying to figure out what the limit as n goes to infinity of natural log of n over n is. We don't know. So what we do is we convert the problem, all right? We say instead, let's look at the limit as x goes to infinity of natural log x over x. So do you see all I'm doing is replacing the n's with x's? Now, these are functions from Cal 1. Now we can use L'Hopital's rule. This still is infinity over infinity, right? So by L'Hopital's rule, this is equal to, and you can put an L or an H here. It's up to you. I always put L. I don't know. The books always use H. I like L. L'Hopital, letting everyone know that's what I'm doing. And what do you do for L'Hopital when you have infinity over infinity? Derivative of top and bottom separately, right? Not quotient rule, right? Separate, derivative top and bottom. Derivative of natural log of x, 1 over x. Derivative of x, 1. So what happens here as x goes to infinity?
0 over 1.
Yeah, so I'm just going to clean it up. This is just 1 over x, right? And that goes to 0, doesn't it? So we were saying if this, the theorem says if this goes to L, right, that goes to L. And this does go to L. What's L? 0, right? This goes to 0. Go ahead.
When it's like squared and stuff, you have to keep taking the derivative, right?
Yes. Well, you can only keep doing derivatives if you continue to have infinity over infinity or 0 over 0. If you ever get to a point where you no longer have that, you cannot do L'Hopital anymore. All right, so here we say therefore. Have we done the 3 dots yet?
Yeah.
Yes? Okay, therefore, this limit as n goes to infinity of natural log n over n equals 0. So for the rest of today and next couple of, maybe next class or so, I'll continue to do this where I will switch over to x, I'll get an answer, I'll come back and make a conclusion. But at some point, I will stop doing that and I will just say, oh yeah, we know we could switch that to x, and it would basically get us to the answer. So because of, I don't know if it's laziness or if it's more like just trying to be quick, I will stop going here. But let's remember that you cannot take the derivative of a sequence. You can take the derivative of a function, continuous function. All right, we good?
Yes.
Okay, let's look at another one. How about this? As an example, does this converge or diverge? question. C and D, converge or diverge? Sequence is -1 to the n over n. Do you remember what -1 to the n does? It switches it, right? Oscillating back and forth between positive and negative, or it could be negative and positive. In this case, let's actually write out what this sequence is so we can get an idea of what it looks like. We start with n being 1. We get -1 to the 1, so it's -1 over 1, so -1. And then the next term of this sequence, or next positive a half. Then -1/3. We're not square. Just plugging in n, right? Then +4th, -5th, +6th, so on and so forth, right? That's what that sequence looks like. Now, if I were to actually graph this sequence, when I plug in 1, it spits out -1, right? I'll put it here. When I plug in 2, it spits out, what, a half? And then 3, -1/3, 4, +1/4, 5, -1/5. See that? What's happening? What does it look like is happening? It's going towards 0, right? It's going towards 0. How are we going to conclude that, though? I mean, we can see it visually, can't we? But we need to. I mean, can we do this limit? Can you use L'Hopital? No, because it doesn't do infinity. It's not infinity over infinity, right? It's not 0 over 0. So what is happening? That's yes, but I'm saying, how can you draw that conclusion without the picture? Like, because we need some way of
Absolute value.
take the absolute value of this.
See if it equals 0.
Okay, and if it does,
Then it converges to 0.
how do you know?
I just removed that.
Okay, good. I'm glad you remember that, because that's the next theorem I'm about to give us. Okay, so the problem here is that we know. Look, do you agree that if this was just 1 over n, we would all say the answer is 0?
Yes.
Right? Because, well, we knew this back from, I mean, it's just basic number sense, right? I mean, fixed number on top, bottom gets huge, this thing goes to 0. But does the alternating part of this have an effect? And the answer is, well, maybe, maybe not. In this case, no, it won't. But the theorem that I'm about to give you is what's going to allow us to knock it out pretty quick. So here's what the theorem says. And this is theorem 6 on page 429. It says if the absolute value of a sub n goes to 0, then a sub n goes to 0. So please refer to last class. When I use this arrow right here, what that really meant, okay, what this really means is I'm saying limit n goes to infinity, absolute value of a sub n equals 0. That's the short way of telling you that the limit of this sequence is 0. We just draw the arrow instead of writing all the limit stuff down. Okay? So if this limit goes to 0, then that limit goes to 0. All right? So for this theorem, for this example up here, what I'm going to do is this. Let's look at the absolute value of -1 to the n over n. Let's look at the absolute value. Now, what can you tell me about the absolute value of -1 to the n? It's always going to be 1, right? No matter what you plug in for n, this is either going to spit out a positive or a -1. And when I take the absolute value of that, that's always going to be +1, right? So I go, you could do it this way, -1 to the n absolute value over absolute value of n. That's 1 over absolute value of n, like that. And what about the absolute value of n? Do I ever have to worry about n being negative? No, because n's going to start at 1, then go to 2, 3, 4. So I don't need the absolute value bars around the n, do I? And so the absolute value of the sequence, right, is equivalent to 1 over n, and we know that that goes to 0, right? Therefore, absolute value, -1 to n, which equals 1 over n, goes to 0. And by theorem 6, that means -1 to the n over n also goes to 0. So if the absolute value of a sequence goes to 0, then the sequence itself must go to 0. Got it? Understand? We drew the conclusion right here. Put what? I would get used to, yeah, I should have told you all this a while back. One of the things that I'm going to be looking for on the next test, and it's going to be almost inherent in the problems, is that you're going to have to, all the problems that you're going to get that are going to involve these series and stuff, you're going to be basically figuring out if they converge or diverge. It's basically one of two answers. It converges or diverges. What I'm looking for is your justification as to why it does one or the other. And so you have to be able to logically go through step by step explaining why you're drawing your conclusions. So all this stuff I'm writing in here is something that you will need to write also. You can't, if you just gave me this problem, you just put equals 0 and that's, or limit is 0, and that's it, and there's no work for it, you don't get credit for it. So it's not about just getting the right answer, because then you can just flip a coin and hope for the best, right? You understand what I'm saying? We're going to have, for the series, we're going to have these things called series tests that we run. And the test is a test to tell you whether or not it converges or diverges. And within these tests, you have to run the test properly. You know, and it's, if you don't run the test properly, you can draw a conclusion of false, you know, false positive, false negative, whatever. You know, all these different things could happen. But if you're not showing your work, then I have no idea how you're drawing your conclusion, right or wrong. You'll see. All right, let's look at another question. How about this one? Does this one converge or diverge? Converge or diverge? A sub n equals -1 to the n times n over n plus 1. Any ideas? Tell me what you want to do here. You want to write out some of the terms? Okay, that's fine. What's my first term? -1/2. Right, n equals 1, get -1/2. How about 2? What if n is 2? It's a positive, right? Because -1 squared is positive. Then you get 2 here, and then 2 plus 1 is 3, so 2/3. Next one. -3/4. Next one. 4/5. Next one. -5/6. They just keep on going up by 1, right? Top and bottom, numerator and denominator, keep on going up by 1, but they keep switching signs also. Does that converge or diverge? What is that? Converge to 0? Diverge? So we're getting different answers here, right? Do you want to try and draw these? Let's see. Here's -1, here's +1 right here, okay? If you plug in 1, you get -1/2. If you plug in 2, what do you get? 2/3. If you plug in 3, -3/4. 4, 4/5. Is it going to keep getting bigger, or it gets closer to 1, doesn't it? It gets closer to 1. Check this out. It's like you have an asymptote up here and here. So it looks like, right, because no matter what you do, the denominator is always bigger than the numerator, right? If your denominator is always bigger than the numerator, your ratio is always less than 1. Agreed? So it's getting closer to 1. It's never going to get there, but it's switching back and forth. So does that converge or diverge in your mind? It diverges. Okay? To converge, you must go to a single value. You are not going to a single value here. You're oscillating back and forth. You're getting closer to 1 sometimes, but then on other values of n, you're getting closer to -1, right? Now, let's try something. What if we take the absolute value of this? What would happen if we take the limit as n goes to infinity of the absolute value of this sequence? So, I forgot that in here. So what does the absolute value of that do? What can you eliminate from that? The -1 to the n? Doesn't matter anymore, right? Then you have n over n plus 1. Do you need the absolute value around that? Can that ever be negative? N over n plus 1? No. So that's the same, isn't it? So what is this? What is this limit? That's infinity over infinity, isn't it? So you could do L'Hopital here, couldn't you? But you'd have to switch it first, right? So there's a little sub-thought here. From here, I'd say I'd look at limit x goes to infinity of x over x plus 1, which by L'Hopital's rule is limit as x goes to infinity of 1 over 1, which is 1. Right, derivative of top and bottom is both 1. So your answer is 1. So this answer is 1. So what? Converges. Why does it converge? The absolute value converged to 1, right? What does the theorem say?
The absolute value is a set number themselves.
Is that what it said? That's right. Be real careful with this theorem. That's why I'm giving you this example. The theorem says if the absolute value of the sequence goes to 0, the original sequence goes to 0. But if the absolute value of the sequence goes somewhere other than 0, that you can't draw a conclusion at all. Okay? So this doesn't tell me anything. That theorem I just gave you does not work for this problem. Understand? Does not work. So yeah, so how are we going to, so theorem 6 does not apply. Since that is not 0, right? I could put in here, this is not 0, so theorem 6 doesn't apply. So that was a good try, but it didn't really help us, did it? Right? Still kind of have an open question here, don't I? Kind of have an open question. So, trying to think of what I want to do to show you this one. Let's do it this way. We know that n over n plus 1 goes to 1, right? And -1 to the n alternates. The sequence. And we're going to draw a conclusion in words here. We're not really going to do anything else. We're just going to write down what we're thinking, right? In order for it to converge, it has to go to a single number, right? So all I'm going to say here is, look, I'm getting closer. This part of it's getting closer to 1. This part's making it switch back and forth. So there's no way that it can converge to some number, both a positive and negative number, right? So since these answers, or since these alternate between positive and negative numbers, and this is important, and get closer to 1 and negative 1, the sequence must diverge. It would be impossible for it to go to a number if it always has to get closer and closer to a positive and negative number, switching back and forth. Now, the reason why I said and gets closer to 1 and negative 1 is because look at this sequence we had before. It did this, right? Did that one converge? It converged to 0. Aren't these switching back and forth between positive and negative? So that's not enough to say it diverges. You needed the fact that they were also getting closer to 1 and negative 1. So they were spread out, right? These were actually funneling down to 0. Okay. Another theorem. Maybe we should look at an example before I do it. Yeah, I'll look at an example before I do it. And then we'll probably get stuck. How about converge or diverge for this one? A sub n equals n factorial over n raised to the n. That's an interesting sequence. Let's try and write out some of these, all right? Hold on. Yeah, that's what I wanted. Okay, what would you get if you plug in 1? What's 1 factorial? 1 over, what's 1 to the 1? 1? So that's just 1. Okay, plug in 2. What's 2 factorial? 2 times 1. Now, I know I don't need the 1, but that's what it is, right? And then on the bottom, 2 squared. Agreed? Which will be 4. Yes, I agree. Next one, 3 times 2 times 1 over 3 times 3 times 3. Agreed? 3 cubed. 4 times 3 times 2 times 1 over 4 times 4 times 4 times 4. And so on and so forth, right? I hope that that's obvious that the top is headed to infinity and the bottom is headed to infinity also. Yes? They get larger and larger. So this is headed to something like infinity over infinity. So that may make you think L'Hopital. But what's going to be the problem with L'Hopital? What's the derivative of x factorial? Well, you can't do that because, see, the whole idea behind that theorem was that if I'm looking at a sequence like we did the natural log, then we came in with those dots in there. We said, well, wherever the natural log goes, the dots have to go also, right? The problem with n factorial is that n factorial is not defined for values like 1/2, pi. You can't plug those things in. So there is no red part, there is no red curve that I can draw for n factorial. So you can't switch it to real numbers. Understand? You're stuck in integers. So L'Hopital is out the window. Got it? Now let's go back here and let's just rewrite this and see we get. Notice that those 2's canceled and I get 1/2, right? These 3's cancel, I get 2/9.
Can't you just prove it by just looking at it more like? Because like
what are you going to,
1, but from there you keep going less than 1, right?
you get 1.
Because so then like the less than 1s are outweighing the 1. So we, like it's always 1, it's always 4 over 4 at the beginning, so it's 1. But then everything else in that keeps going closer and closer to 0.
Yes, I agree, but we need a more formal way of doing that. I'm going to do it in just a second. So you want to see the pattern first. That's what I'm trying to get you to see here. You see how this is canceling, right? And then this one right here, 3 times 2, look, I'll just write 6 if you want. 6 over 64, and then I could keep going, right? So it looks as if it is converging, right? It does look like it is getting smaller. It looks like probably 0, but I need to prove it. I can't just say, yeah, it's obvious that it does. Okay, you have to have a way of proving it. We can't use L'Hopital. It's not like the last problem where I could just kind of justify it by saying, hey, look, it's headed between -1 and 1 back and forth, right? Alternating and staying away from 0. So what we use for something like this is the next theorem, which is called the Squeeze Theorem, which you are probably familiar with from Cal 1. Squeeze Theorem. And here's how the Squeeze Theorem works. Have I put that up here for y'all before? Suppose. Okay, that's the alternative for writing the word suppose. All right? Got it? All right, suppose that you have a sequence A sub n, all right? And I can tell you that that sequence is always bigger than or equal to some other sequence B sub n. So B sub n is some other sequence. And I also know that A sub n is less than or equal to some other sequence C sub n. If B sub n goes to L and C sub n goes to L, then what do you think happens? A sub n must go to L. So here's kind of a picture of what's happening. I have 3 sequences, right? 3 sequences. And I'm just going to make these up completely. The B sub n, I'm going to do this one in blue, all right? I've got some sequence, and I need to pick an L, so let me pick an L here. Here's L. I'm just going to imagine this dotted line that goes this way. And what I have is that B sub n goes to L, right? I'm assuming that B sub n goes to L. So that means B sub n does some stuff. Could B sub n do this? Could it do that? Would that mean B sub n is going to L? Yes? Okay. And then I'm going to have C sub n also goes to L. But C sub n is bigger than B sub n. Do you see that? So that means it always has to be above, right? So far, is C sub n okay? C sub n okay? C sub n okay? C sub n okay?
Yeah, it's above L.
Is it above B sub n? That's what that means, right? Okay, but hold tight for a second. Is B sub n going to L?
Yes.
Yes? So you agree with me that in my drawing, this is true, right? And this is true, yes? B sub n and C sub n are going to L. But this inequality is not true at that one point, agreed? But as I went out further, it was okay. So there was really only one place where it violated that inequality. Okay, I have to come back and address that, but just hang tight with that idea. Now, A sub n, we're supposing that A sub n is between these two, all right? The conclusion is that A sub n always has to go to, that it has to go to L also. So let me draw A sub n right here. Is A sub n between the two? Yes? Yes? Okay, is A sub n between the two? Is A sub n between the two? No. Okay. Is A sub n between the two? No. Here? 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 Here. So what I'm trying to get you to see here is that the way that this theorem works is that it's trying to tell you what's happening way out here as n goes to infinity. All right? That's what it is talking about. You might have some screwed up junk in the beginning. You might have where this is not true. All right? But eventually you need this to be true. And if this is true, and these two go to L, do you agree that the A sub n must get sandwiched between the two? Yes? No? No? Yes? So what I'm going to do is I'm going to write one more thing next to this. Suppose B sub n is less than or equal to A sub n is less than or equal to C sub n eventually. What I mean by eventually is that there is some capital N here that once I get past capital N, that holds. All right? So this inequality is true for little n greater than or equal to capital N. I know you can't tell my capitals and my little n's apart from each other, but this is a capital N, okay? Y'all seem tired or stunned? I'm not sure what it is. Huh?
First one for me.
What did I say first? Oh, tired. Stunned? Okay, so the squeeze theorem creates a funnel. And the funnel smashes the thing you're interested in between two things that you know. In the beginning, it may not be true that the inequalities hold, but you need it to eventually hold. For a big enough n, capital N, then they've got to follow the pattern. And then once you follow that pattern, it can't change. And then it will funnel it, okay? The reason that I want to address this is that we will have some sequences that in the beginning they don't actually behave the way we need them to, but if we let n go to infinity, they will. They will follow the pattern. All right. So in this problem, using the theorem, the way we use it is this. This is the target sequence. This is the sequence that we're trying to figure out. All right? We are asked that in the beginning of the question. The beginning of the problem is that's given to us. Where does it go? What's its limit? We have to come up with two sequences that we can squeeze it between. And those two sequences both have to go to the same value. If they don't go to the same value, this theorem is out the window. So let's go back to the one that we were working on a second ago, which was n factorial over n to the n. So my A sub n is n factorial over n to the n power. Right? I'm going to write that out in a different version, which we didn't write before. Do you agree that this is n times n minus 1 times n minus 2 times n minus 3 times dot, 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 all the way until I get down to 1? Yeah? You agree with that? And then on the bottom, it's what? N times 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 n times, all the way till I get down to what? No, it's not a factorial. N, right? Just n. How many of these guys do I have here? N. I have n n's, right? That's how many n's I have there. What does n raised to the n mean? N times n times n, n times, right? Are we okay with this?
How come it wouldn't be infinity?
I'm not letting n go to infinity.
Okay.
I'm just rewriting this, right? If I said what's a sub 4, you would go 4 factorial over 4 to the 4, so it would be 4 times 3 times 2 times 1 over 4 times 4 times 4 times 4, right? So I'm saying right now, let n be n, but don't let it go to infinity. Then this is what we would have. Yes? Yes. Okay. I'm going to try and squeeze that between two things now. All right? Where did we think it was going? Where did we think this sequence was going when we wrote it out? We thought it might be going to 0, right?
Yeah.
So as a lower bound, I'm going to say I'm going to say 0. Would you agree with that? These are all positive numbers on top, right? These are all positive numbers on the bottom. That's definitely got to be bigger than or equal to 0, correct? Yeah? You see what I'm doing? Okay, now, this is b sub n. This, of course, is a sub n, this thing right here. Right? I've got this. Now what I need to do is get something. I've got to pick something that's going to be bigger than this, and I have to be able to convince you and myself that it's bigger than that, but it also needs to go to Squeeze theorem. We want these two to go the same place. Where does this head?
0.
0. There's no changing that, right? Whatever I use as this upper bound here, it's got to go to 0.
So this is 0.
This can't be less than 0, right? Because it's all positive numbers. Okay, so now let's get to the pattern that you saw, all right? Does everyone see that this number right here is 1? Okay, so watch. Here's what I'm going to write. I think so I don't have to write this all down again. I'm just going to write this down. Do you agree that this right here is equal to 1 times... Now tell me about this number. N minus 1 over n. Is that number bigger than 1 or less than 1?
Less than 1.
Less than 1. Guaranteed, right? The numerator is smaller than the denominator. Do you agree that's less than 1? So this right here is 1 times a number that's, I'm just going to use this for notation. This is, how do we want to say this? Less than 1? I don't know how you want to say it. That next number, though, that I'm multiplying by is smaller than 1. Yes? Times, what about the next number? It's also smaller than 1, right? So this next number is smaller than 1. Times this next one, it's also smaller than 1, isn't it? And I keep doing that all the way until I get to the very last one. What's the very last one? 1 over n. I agree that that's smaller than 1, right? But it's also equal to 1 over n, isn't it? So I can say times 1 over n. Do you follow me so far? This big, nasty, ugly thing is equal to 1 times a number smaller than 1 times a number smaller than 1 times a number smaller than 1, all the way until I get to 1 over n. So that definitely has to be smaller than 1 times 1 times 1 times 1 times 1, all the way until I get down to 1 over n, doesn't it? If each one of these is smaller than 1, if I multiply them, it's smaller than 1. So all this junk in here is less than 1. So, yes? Y'all see it? So this is all 1 that's bigger than all that other junk. So all of this is less than 1 over n. Got it? So what I'm going to do now is I'm going to take the limit of each one of these. And the inequality has to hold. The limit as n goes to infinity of this sequence, which is 0, so nothing's going to happen, it's just going to go to 0, must be less than or equal to the limit as n goes to infinity of this sequence, which I'm going to write it the other way, n factorial over n to the n, must be less than or equal to the limit as n goes to infinity of this sequence, which is just 1 over n. Do you all see how I created the upper bound on this sequence? Do you all see that? Now, this goes to 0, of course. That must be less than or equal to the limit as n goes to infinity of n factorial over n to the n. But that must be less than or equal to the limit on that one. And that one's the obvious one, right? 1 over n, that goes to 0. And therefore, there's only one place that limit can go. If it has to be squeezed between 0 and 0, it's got to go to 0. Therefore, the limit as n goes to infinity of n factorial over n to the n is equal to 0. I think I'll give you one more of these that'll be a little bit easier to do. Got it? How about this one? Converge or diverge. A sub n equals cosine squared n over, oh yeah, well, no, I'll just do cosine n over n. Let's try and, you can do this one with L'Hopital. You could, because the cosine of x, and that's a nice function. You could do, well, you know what, could you do L'Hopital? Is it going to infinity over infinity? Hold on, I take that back. What does cosine of n do as n goes to infinity? Just keeps oscillating up and down, right? So it doesn't, you don't get infinity over infinity here, so you can't use L'Hopital. Let's try Squeeze theorem. So when you look at this right here, is there any sort of bound that you can put on any part of that? Like, is there anything that you look at there and you go, oh yeah, I know that's between this and this? What is between -1 and 1? Cosine. So I'm going to start with this. I'm going to start with what I know. This I know for sure from pre-cal, right? Absolutely, for sure, that's true. I'm going to start with that. And now this doesn't work for the squeeze theorem because the middle piece is not what we're looking at, right? Not to mention the edges, the two bounds, don't go to the same place, right? This goes to -1, this one goes to +1. So I would not be squeezing here, would I? Okay, what do we need under this in order for it to match that? I need an n, right? Divide by n? But you have to divide everything by n. So divide by n, divide by n, divide by n. Now, you do need to be careful because with inequalities, if you divide by a negative number, what happens to the inequality? It flips. But n here for us, since this is a sequence, is always positive, isn't it? N is 1, 2, 3, 4. So we don't have to worry about flipping inequalities here. So that's still true. And I believe that's all you need. Right? Do you see, if you take the limit, I'm just going to do shortcut here. If I do limit here, limit here, limit here, right? Limit of this one as n goes to infinity is a fixed number over something that becomes infinite. That goes to 0, doesn't it? Yeah. So this goes to 0. This one, we just did, goes to 0, and which means the one in the middle has to go to 0. Cosine n over n must be less than or equal to 0. All right, one last type of thing you may run into here. Suppose a sub n equals r to the n, with r being greater than 0, r being a real number. Here's what we get. R sub n, or sorry, r to the n will go to infinity if r is bigger than or equal to 1. Hold on a second. No, that's not true. If r is 1, there, r to the n will go to 0 if r is less than or equal to 1. less than 1. Strictly less than. What if R is 1? Yeah, think about if I gave you this sequence. A sub n equals 1 to the n. What is that sequence? 1, 1 squared, 1 cubed, right? Does that converge or diverge? Converges to 1, right? It is always 1, right? So in the case that R is bigger than 1, this thing will become infinite and therefore diverge. If R is less than 1, then it'll go to 0. If R is equal to 1, then it converges to 1. Now, let me give you some examples of this. An example of this would be A sub n equals 1/3 to the n. Does that look like that type of sequence? Yeah? What's R here for us? R is 1/3. R 1/3 is less than 1. This will converge to 0. You do not have to explain that. You don't have to justify it. You can just write it down from here on out. Just identify what R is. You can say, okay, this is my sequence. R, that's less than 1. Therefore, it, this thing goes to what? 0. Here's another one. A sub n equals pi to the n. So R is going to be pi here, which is greater than 1.
Yeah.
Therefore, A sub n equals pi to the n diverges. You can just say diverges. You don't have to say it goes to infinity. Divergence is good enough. All right, we good? All right, so when it comes to finding the limit of a sequence, there's lots of different things that can happen. You can wind up just doing a limit and everything works out. Last class, do you remember I gave you that one where you had to come in and do something on the top and bottom, pass it through a root? You can go look at last class notes. Okay, so we have that. We have L'Hopital's rule. We have the theorem that if the absolute value of the sequence goes to 0, then the sequence goes to 0. We have Squeeze Theorem. We've got this. I mean, all those things are in play now, and you should be able to handle the homework problems that I assigned last time. All right? We're not done with this section, but the section kind of has two parts to it. Limits of sequences, which is what we've done now, and then what I'm going to talk about for the rest of the class, which are some other properties of sequences. All right, so this is some definitions. What is what's called an increasing sequence? What do you think an increasing sequence is? It gets bigger the further you go out, right? Yes? That's exactly what it is. But here's the way I write it. A sequence is increasing if A sub n is less than A sub n plus 1. So just think about what that's saying. It's saying that A sub 1 is less than A sub 2, but that's less than A sub 3, which is less than A sub 4, which is less than ... which means the further you go out, the bigger they get. So it increases if you were to look at, plotting the dots. Understand? Decreasing sequence is the opposite, right? If A sub n is bigger than A sub n plus 1, then we call it decreasing. So a sub 1 is bigger than a sub 2, which is bigger than a sub 3, which is bigger than a sub 4. So as you move from left to right, these dots get smaller and smaller and smaller, right? Do you have any questions about visualizing that? Okay. In either case, all right? In either case, I don't know where I can put this. In either case, these are called monotonic sequences. So if I tell you that, if I tell you right now that, hey, I've got this sequence, okay, and it's monotonic, and that's all I tell you, then that means it's either increasing or it's decreasing. But you don't know which one. Next definition. Bounded above. A sequence A sub n is said to be bounded above if that's the mathematical symbol for there exists. If there exists a capital M such that A sub n is less than less than capital M. I'm running out of room. And this is another symbol you probably have never seen for all n. It's an upside down capital A. This is a backwards E. Those are probably not going to be used in your book, all right? But that's what mathematicians use for those words, right? So no harm in showing those to you. That's okay? No objections? Does this make sense? You have a sequence, right? All these dots. Saying it's bounded above means that there's some number, right? M, capital M, that your sequence always stays below. So your sequence, every single number in your sequence is always smaller than that M for all n's. So if you plug in 1, it's going to be less than M. You plug in 2, that number is going to be below M. Plug in 1,000,000, it's still going to be below M. So it's bounded above. It has a ceiling, right? A roof that it never goes past. As you might imagine, after we talk about bounded above, what would come next? Bounded below. So bounded below works like this. Bounded below. A sequence A sub n is said to be bounded below if what? There exists, right? Instead of a capital M, we use a little m. This is like the one time my handwriting really sucks because I can't distinguish capitals from lowercase, all right? So if you've got a way of distinguishing your caps from your lower, then do it. I just write mine smaller. There exists a little m, all right, such that what? A sub n is greater than A sub little m for all n. So A sub n is greater than little m for all n.
Are you giving us examples? Or are you just telling us?
Yeah, we're going to look at some.